Yeah, hello everyone. My name is Tomek, and together with my colleagues, we would like to present you the recent developments in the Offchain worker area. I think we are a little bit overdue, so I will try to keep it short. So we are not giving an intro to Offchain workers today. If you don't know what Offchain workers are and you want to learn a little bit more, then go and see these two videos. I hope that the slides are being shared with you, so probably you will have the links, or just copy the titles and just try to look for that on YouTube. Basically, the thing that you need to know today is that the Offchain worker is like a separate application running alongside your blockchain client. So it lives outside. It is triggered by every block that is imported. It can do some processing. It can do some external calls, some external side effects, like fetching something from HTTP server, and then it can submit results back using a transaction. So it doesn't have a direct access to modify the blockchain state. And Offchain workers are these off-chain applications, but kind of built in to Sub0. So when you are writing your runtime, you can very easily write your off-chain worker code, and then everyone else running your client can just opt in to run them, and they are being upgraded at the same time as your runtime is. So why is that useful? When we are building Offchain workers infrastructure, so all the things around Offchain workers, we are basically focusing on the three use cases that you can see here. First of all, blockchains are isolated, so there is no way to get some real world data. You usually do that through oracles, and Offchain workers can be used to build such oracles in your blockchain. Secondly, any heavy computation. This is not something that you want to do during block imports, because this is something that everyone in your network will have to do, and it's super wasteful to do any very difficult computations there. So some stuff can be offloaded and run or off-chain. And third use case is, since Sub0 doesn't store many indexes by default, basically you can only get blocks by hash and blocks by number, and that's it. There are use cases where you actually want to have more data index. Let's say you want to know all the transactions that are in your blockchain, and I have some way to retrieve them. And hopefully you can use Offchain workers to build this kind of indexes into your chain. So what did we add recently? There are a couple of things that deserve mention today. So we have added support for no standard environments in Ser.json. So it means that you can now use Ser.json when you are deserializing or serializing your HTTP request in your Offchain workers, because it compiles to WASM. We are still waiting for all Ser.json to be released, as far as I know. There is an easier access to Offchain database through storage value API. Internally, we have moved fragment elections off-chain. So before it was being done at the very end of the session, as far as I remember. Right now, there is the whole fragment computation is done off-chain, and then only the result is submitted as a transaction. And we are working on introducing equivocation reporting as an off-chain worker as well. Today, we will cover 4 other additions. I will cover transaction source, then Rakan will tell a little bit more about new signing and transaction submission API. Bernhard will tell us a little bit about runtime indexing API, and Igor will tell us about upcoming, hopefully pretty soon upcoming support for async await for Offchain workers. Okay, transaction source. So on this diagram, you can see how the transactions flow within the client if you are running a validator node. So most likely every block import is triggering Offchain workers, and most likely these Offchain workers are producing some transactions. These transactions end up in the transaction pool, And periodically, from the transaction pool, there is a block authorship component that will retrieve transactions that are scheduled to be included in a block in the transaction pool, and then it creates a block out of them. That block is imported, and the cycle kind of closes, because then we run off-chain workers for the next block. But obviously, this is not the only source of the transactions within Substrate node, because we have some that are produced locally by our off-chain workers, but most of the transactions are actually retrieved or received over the network by listening to these gossip messages from other peers. And so far, without this transaction source API, there was no way to distinguish one from the other. So let me go into details what I mean by that. So every transaction that the node sees goes to the transaction pool first. The transaction pool is a generic component that doesn't really know what the transaction is at all. It's just like raw bytes for the transaction pool. So the transaction pool has to ask the runtime, so the thing that you are writing, hey, can you tell me if this transaction, if this blob of bytes is actually a valid transaction, and what properties does it have? So we call into the runtime and we ask if the transaction is valid. And currently, the runtime wasn't able to tell if that transaction was received from the off-chain worker, or was it received from the network itself. So we have changed the API, and you can see that previously you were implementing a trait called tag transaction queue, and it only had one method with one parameter, which was just extrinsic, so the transaction itself. Right now, there's an additional parameter called transaction source. It's an enum and has like 3 values as far as I remember. So why did we do that? So first of all, now you have the ability to actually see that the transaction was produced by an off-chain worker, and then change the behavior of your validation function. So for instance, you can increase the priority of that transaction, or you can accept only transactions that are produced locally and not the one that you receive over the network. This enables us to use unsigned transactions in the network, especially by validators, without risking a DOS vector. I will go into more details on the next slide. And having this unsigned transactions included by block authors is a way to have their opinions on things included without any cost. So it's very similar to inherent mechanism that we also have, but it's less strict, so it's more easy to opt out from. So let me briefly tell you what kind of transactions we have in Substrate. So the regular transactions that you most likely everyone is sending is a call wrapped in a transaction and then a signature assigned to that transaction. So it's easy to figure out who sent that transaction, and we can charge fees if that's the case. Other kind of transactions are unsigned transactions. So this is just a call wrapped in a transaction without a signature. So we don't know who is sending that. We don't charge fees in that case. And then it's really interesting it's really important to get the validation logic right, because otherwise everyone can produce these transactions and you may spend a lot of time to validate if they are valid or not. Since usually we want only validators to send these unsigned transactions, we had to come up with a different mechanism to enable that before transaction source, which was an unsigned transaction with assigned payloads inside. And that's something that I hope Rakan will be able to tell you a little bit more about, because that's it from my side on the transaction source. Rakan, would you like to take over? You have to unmute it, yeah.
Can you guys hear me?
Yep.
Okay, cool. So hello, everyone. My name is Rakan, and I'll be presenting the changes we've made in signing and transaction submission APIs. So to start off, we begin talking about the problems we've observed in the previous implementation. First of all, the APIs we had enabled submitting either signed or unsigned transactions. Each of those had its own problems, like namely submitting signed transactions provided minimal control over the accounts with which you could sign the transaction. Submitting an unsigned transaction had a potential attack vector, which Tomek just talked about in his previous slides. In addition, there was some level of internal and external complexity that we had to address. So the goals of the goals for us were to address the issues we just talked about. Other than the fact that you could still submit signed and unsigned transactions, we now enable the ability to submit unsigned transactions with signed payloads to address the attack vector we previously had. For signing transactions, we've introduced some APIs to give the caller more fine-grained control over the accounts used for signing. And lastly, simplified the way signing is implemented in the runtime and the tests. So what have we changed exactly? We've introduced some additional runtime level types and palette level types, as you can see, where those types have to be implemented in order to submit transactions depending on the use case. We'll go over the details of each of those types in the next slides. So the simplest use case to talk about is basically to submit an unsigned transaction. Previously, or in the previous implementation, we required that you define your an associated type in your trait that you would use to submit an unsigned transaction. In the new implementation, we basically just require you to import the submit transaction type, and then you would call submit unsigned transaction, and this is how you submit the unsigned transaction itself. Moving on to the second use case, which is submitting a signed transaction. The code here is a little bit more involved. Initially, what you have to do is in your palette, you have to generate app-specific key types to be able to use those keys for signing. And we've introduced the signer struct, which you could use to submit, sign and submit transactions. So in this example, we're using the signer type to submit a signed transaction. There are multiple things to pay attention to here. Notice how we provide the signer with the types, or let's begin with any account. Basically, what we are doing here is we're satiating a signer by calling any account. I'll explain what any account does in a bit, but also notice that we are passing signer the types T and T authority ID. T in this case is the palettes trait that you've implemented, and the T is required to implement the system trait. T authority ID is a crypto type that allows the signer to query the key store for all the accounts that match the authority key type ID. So by calling any account here, we tell the signer that we only want to use any available key that match basically the authority key type ID to sign the transaction. And lastly, what we call here is send signed transaction, where we pass a closure parameter that gets the account with which we're signing the transaction, and the closure is expected to return the call that is submitted on chain. Yeah, so this is basically the last example that we're going to give, which is about submitting unsigned transactions with signed payloads, and this is what this is basically the new functionality that we've introduced here. It's very similar to the way we sent unsigned transactions, or sorry, signed transactions, but in this case, what we're doing is calling send unsigned transaction, and we're passing two closure parameters. The first one is expected to basically return the payload which the signer is going to sign. The second closure gets the payload that the first closure returned, and the signature that the signer calculated for the payload. And the second closure is basically expected to return the call which is going to be submitted on chain. Yeah, so let's move on to the next slide. So in the previous slide, we there was in the code example, the fact that we submitted, or the first closure, if you paid attention, it returned the price payload. On the right-hand side of this slide, what we show is how we define the price payload, and it's basically a struct that our palette defines, which holds whatever information that we need to record on chain. And on the right side, we show like the trait that should be implemented by the struct, which is signed payload, and we only require the implementation to provide the public key. And in this case, notice how signed payload handles signing and verifying for you. So this concludes the palette level traits that we have to implement. This concludes the list of things that we have to implement on our palette level. And we right now are looking at 2 additional palettes that we have to implement on our runtime to be able to submit transactions. And the third one is, if we go to the next slide, also shows a third type, which is create signed transactions. So the 3 types that we're showing here, signing types, send transaction types, and create signed transaction, the purpose of those traits is basically to be able to know on the palette level what concrete types that are being provided and used on the runtime level. In this case, we're showing create signed transaction, and this trait basically existed before as create transaction, but it's basically been renamed to create signed transaction. The logic inside the create transaction method is basically, or it's exactly the same as you had before, if you've already had it in your palette. However, we wanted to shed light here on the fact that the trait definition and the create transaction method signature are now different. And that's pretty much it. I think we've covered most of the changes. It is possible for you to look at the example Offchain worker palette to be able to look at more complete code samples on how to implement this in your code base. And that's it. Thank you very much.
Okay, let me invite Igor on stage now. Igor will tell us a little bit more about async await, hopefully. Yep, he's here. Okay, great.
Hey. Hello, everyone. My name is Igor, and the question is, can everyone hear me? Hopefully.
I think so. I can hear you.
Okay, that's good. Let us start in. So today I'd like to briefly introduce you to the upcoming async await support in the Offchain workers. So let's start and get into the current status quo. So as of now, Offchain workers are blocking. And this means that, for example, and once we start waiting for an HTTP request, we cannot do any progress with anything else until it finishes. And internally, the Offchain worker is spawned on a dedicated thread in a substrate runtime, and you can't get any fine-grained control of that. So back to the existing API. Let's see how it looks like in the beginning. So we have our Offchain worker function, which serves as our main entry point. And apart from the business logic, we can also execute low-level I/O functions such as sleep until or HTTP request wait. And under the hood, these can put our thread to sleep or blockingly wait until an internal task on the host side completes. So as we can see, we cannot do any other work while these block the thread that the Offchain worker is using. But, however, this is not to say that the HTTP implementation is entirely blocking. We have an internal HTTP worker on the host side, which drives all of the underlying HTTP requests in an asynchronous fashion. We like to generalize this approach and allow the users to run any asynchronous computation they like in Offchain workers. So here comes our new approach. We'll introduce a new EPO-like mechanism which acts as a bridge between the Offchain workers and the internal asynchronous runtime. This will allow the worker to drive and await their own futures without having to rely on the logic inherent to the host itself. And now on the API surface, we'll introduce a new block on function. This will block on the execution of an asynchronous piece of logic. It's worth noting that it works with a regular Rust future type, such as an async block or an async function call. With this, we can use the familiar Rust async 08 syntax, removing the need for substrate-specific future-like HTTP API. This also opens up the possibility of using existing Rust future primitives and combinators. And while we focus initially on the HTTP use case, it should easily expand to the other use cases such as parallel or asynchronous computation. And that's really all for the progress on the Async 08 support and the Offchain workers. Hopefully this will make using Offchain workers more easier and ergonomic. So thanks for the attention, and coming up next, Bernhard will talk about the indexing API.
Okay, so let me just quickly tell you that the indexing API that Bernhard will talk about was merged recently.
I don't see the slide, so this is a little bit of a blind slide. I'm Bernhard. I'm going to tell you a little bit about Offchain indexing. Offchain indexing is a new API we recently introduced to allow taking advantage of the potentially vast new features with the new epoch-based API. With epoch-based API, you can essentially do whatever you want in your discrete implementation of your blockchain to make available to Offchain workers. And thus, it makes sense that you also need more information in your Offchain worker. And that, in consequence, means you need more information in the Offchain DB. On the next slide, you see like the current state. On the left-hand side, you see the current state of how the transaction pool is handled. You get blocks into the transaction pool, either by placing them explicitly or by gossiping. And then in your runtime, you get a callback for onImport that is being called. And your block then enters the state for blockchain DB. In onImport, now with the new indexing API, you have the option to write arbitrary data, whatever you deem necessary or sane, into your Offchain DB directly. From the Offchain DB there, then you can use it as part either for an Offchain worker or directly via RPC. The API, like on this slide, you see on the left-hand side the Offchain index runtime interface and the Offchain runtime interface. The Offchain index runtime interface is what you would use in your on import or on finalize call. And there you write data. The API is pretty straightforward. It's a simple set and clear. You have a key, which is your identifier for whatever data you want to see in the Offchain database. And clear removes that value again. On the other hand side, this is already pre-existing API. It's just a normal runtime interface of the Offchain worker. On the next slide, you see a discrete usage guide on how to use it, because the interface is always a little bit different from how you actually use it. There's the Offchain index set. You have a key, you have a value, and the same for clear. So on the other hand side, the existing API for the Offchain, there is the local storage get, which you use to obtain key one, the associated data to key one from the persistent storage, which is where all the data we write into the Offchain DB from Offchain index APIs reside. On this slide, you see a implementation for onFinalize, where you store the block number and the associated events that are received into the Offchain DB. And this is a really good use case because it's not guaranteed that after pruning, every every individual event is still available. So this is a guarantee that your off-chain worker and the RPC has each and every event that was recorded, even when it was pruned in the actual blockchain DB, is still present in the off-chain worker DB. There's the other use cases. One is flashing. Currently, you have only the information about the current set of validators, but for flashing, especially flashing as part of an off-chain worker, it is necessary that you also know the past, like the past sets of validators for a particular transaction, and be able to identify who was misbehaving. And this is also possible via the off-chain indexing API. The Merkle mountain ranges is a way of efficiently storing data and pruning it. So, for example, you have kind of a sliding window in your off-chain worker DB of only a subset of what you have in your blockchain DB. So you can kind of mirror most of the information into your off-chain worker, but you don't use double the space. Well, that's just two of the examples. And that's about it about off-chain indexing. And I give back to Tomek, who's going to tell you a little bit about the future of off-chain workers. Thanks.
Okay, great. Thank you so much, Bernhard. So we are running out of time, so I will quickly jump to the next slide and just briefly tell you about the things that we plan to implement still. So we are now in the process of identifying common patterns, and one of them that we already identified is the scheduling of off-chain workers. So usually you want them to run after some event has happened, or like every end blocks, but then there is this grace period where you send a transaction. If it doesn't get included, you want to retry at some point in time in the future. And this kind of things, we want to have a nice API that allows you to do that. Then we want off-chain workers to be to know about the capabilities that are requested. So, for instance, as a node operator, you might want to run off-chain workers, but you might want to disallow them to do external HTTP calls. So you are only focused on this like indexer use case or this computation use case. So if for the node operator, we want them to be able to disable external HTTP calls, but on the off-chain worker side, we want off-chain workers to know that this API, this particular API, is disabled. And then a thing that I'm super excited about that kind of bridges the ePOL stuff that Igor was talking about, to be able to run pieces of computation, so like functions in parallel, like concurrently and within your off-chain worker. This is a slide that I was showing multiple times on other presentations, so I don't want to go into details now because we are over time. And that would be about it. We are available for questions on Discord right after the call. And thank you so much.